Okay, so now we can start. So today we have another new speaker, Cugliandolo. So Letizia is a professor at the University of Marie Curie in Paris. She's probably one of the biggest experts of dynamics in general, and in particular dynamics of user-generated systems. She has a very important paper on the solution of the dynamics of spin glasses in the aging regime, where she was able to give analytical descriptions of the aging regime. And then she did a lot of other very nice works on dynamics in quantum systems, in classical systems, in different regimes. So she's going to give you an introduction to the general properties of dynamics, in particular in disordered systems. And after, so she will give 4 lectures, one more than the originally planned. And after her lectures, we will have another series of lectures by Dave Reitman on mode coupling, which will be a particular application of what Letizia will tell you to glasses. Okay. So.
Thank you, Francesco. Okay, so hello everybody. So as Francesco said, I'm going to talk about dynamics, aging phenomena, and evolution in disordered systems, in glassy systems in particular. So what I'm going to do is I'm going to use the slides today and tomorrow, but I will also write on the blackboard in parallel. And on the third and the fourth lecture that now I have, I'm going to use the blackboard. So the plan of the lectures is the following. I'm going to give an introduction today, and there's going to be a lot of superposition with what Mark in particular said this morning, and Ludovic, Giulio in previous lectures. In any case, I prefer to keep repetition of slides, of even the plots, as you will see, in the presentation, so that if you want to go back and look at these slides on the web page, you can see which is my line of reasoning and follow it, well, hopefully in an understandable way. So today is going to be introduction. I'm going to be quite general, as you will see. And since I need to show you a lot of graphs, this is why I chose to use the slides. The next talk will be about coarsening systems. I will define them today, and I will give you, phenomenology, scaling laws, some analytical solution as well tomorrow. The third lecture will be the more technical one. So for the ones who are theoretically inclined, I think it's the one that you will like the most, probably. Actually, it's the one that I'm going to present in a slightly different way from the one that you could find in lecture notes or review articles. It may seem a useless complication, the way in which I'm going to do it, but I think it's not. I think it's, we have been a little bit sloppy in the past in certain aspects. It was not dangerous for what we were doing, but for certain stochastic processes, a little bit of, being careful in the formalism is needed, and this will be useful to not make mistakes that can be seen in the literature in many papers. Now I'm, like Ludovic, criticizing the literature, but I'm not going to give names. But anyway, as he did. But okay, this is the reason why I'm going to present the formalism in a slightly complicated way. And then the fourth lecture will be about the concrete solution of the dynamics of the p-spin model that Francesco mentioned. This is old work, but still I think it's useful to describe it in some detail. So that will be the content of the fourth lecture, and I will do it on the blackboard, not with all the details because it would take much more than an hour and a half, but at least I will give you hints on all how the steps have to be followed and what has to be done to solve this problem. I have a list of references at the end of my slides, but as you will see, much of what I'm going to tell you is already described in the lecture notes from Lesouche 2002, so this is not new. So this is... you can find them on the archives. And I have to mention that several of the speakers and organizers of this school were students at that school. So Ludo, Giulio, Francesco, Florent, and I probably forget somebody. So that was an important school in the field. And Guillaume, of course, my student Guillaume. He's my first PhD student, so I have to mention this as well. So, okay, so let me go a little bit into the content of today's lecture. So today I'm going to talk about equilibrium against out of equilibrium classical systems. All my talks are going to be about classical physics, but at some points I will mention certain things that can be extended or generalized to quantum physics if you wish to do it. The next issue I will touch upon is going to be examples about out of equilibrium cases. So I will go from single particle problem, very simple case, to many body situations where you have many agents in interaction somehow. So the examples that I will describe are diffusion, Brownian motion, phase separation and domain growth. So it's the introduction to tomorrow's lecture. And then I will go to glasses. There will be superposition with what Mark said this morning. And I will also mention driven systems and active matter, as Lisa also talked about that problem yesterday. But I will not describe anything about active matter, just show you an example and tell to you why this is also out of equilibrium. And by the end of the talk today, I will give more details on the out of equilibrium behavior, and I will tell you which are the features that we would like to describe with models and with analytical calculations, and of course with numerical simulations as well, but if you are analytically oriented, with equations and solutions. Okay, so let me start from the beginning, equilibrium versus out of equilibrium situations. So first of all, I have to set the stage, say with which kind of setting or situation I want to work with. So I can choose to work with closed or with open systems. I can choose to work and see whether these systems go to equilibrium or stay out of equilibrium, for which reasons, and then discuss a little bit individual or collective effects. So let me first say a couple of words about closed systems that remain out of equilibrium or that are set to be out of equilibrium in some way. I want to mention this fact because it's a problem of interest which is very much studied nowadays in the quantum context, in the context of descriptions of cold atom systems which are supposed to be quite isolated from the rest of the world. And there is a lot of activity of papers and numerical simulations or solutions of certain models in that context, and there is not so much of interaction. There a little bit there is, but not that much interaction between the communities of the classical and the quantum people. So questions that they ask are very similar to questions that we ask, and maybe we can gain both groups from exchanging ideas and talking to each other a little bit more. So closed system. So imagine that you have just some system which is isolated from the rest of the world. So I draw it with this square here, and it's closed, no interaction. And the question that you would like to ask is if you let it evolve with, say, Newton dynamics, say it's a classical system, so it's just mechanical problem, you let it evolve, and you want to know if this problem that evolves at constant energy, because it's closed, so energy, that will write it like this, is constant. So in a phase space kind of picture, you have some surface in the phase space, and you have a point which represents the initial condition for your system, and this will evolve somehow to some trajectory. And what you want to know is whether in the long time limit you will cover the full surface of this constant energy surface with this dynamics. Okay, so if you do, you say that you have reached microcanonical equilibrium with your problem, but this is a question that is never answered actually in concrete problems. You never really go and look and solve the problem and see whether it really covers the full surface of the phase space in this way. You assume it. When one does statistical mechanics, usually we say, well, after some long time I can assume that I have visited more or less in a uniform way all this surface, and then I assume microcanonical distribution, equal probability for each of the configurations on this surface, and then I go ahead. This is Boltzmann's proposal more than a century ago. So the question of how do I reach this asymptotic state, let's say, belongs to ergodic theory. It was a problem that was kept for a long time in the mathematical physics and mathematical community, and we didn't really care about that. Now this problem came back, in a sense, as I told you, because of these dynamics of quantum isolated systems. The questions that people ask in that context is, imagine that you initialize your problem in this way. I mean, it's a quantum problem, but let's use this image anyhow. So you initialize your problem, and then you do a quench. Quench is the same word that we use in our context, and that I will define in a second. So a quench, in the case of the isolated problem, corresponds to changing a parameter in your Hamiltonian. So your system, this one here, is described by some Hamiltonian. Imagine that it depends on some parameters. We call them lambda. And that at a given time, that I will call 0, I change lambda from lambda initial, let's say, to lambda final. And I let the system evolve under the new conditions of the new Hamiltonian with the new lambda final. And the question is, well, it's the same as the one that I posed before. Is an equilibrium measure reached after some time or not? So this is a question that is very much studied nowadays in the quantum context. You have to consider Hamiltonians which are operators, states, so on and so forth. But we could ask roughly the same kind of question, in the context of classical systems, of course. You have a Hamiltonian, you change a parameter, and you see what happens in the subsequent evolution of your system. So this is why I say that, well, there is some kind of revival of interest in the dynamics of closed systems, and I think that Dave Reichman may talk a little bit about this by the end of his talks. But I'm not sure about that. I may, perhaps if I have time, make some comments at the end of the fourth lecture, but I just wanted to make this remark to start with before going to the case of open systems, which is the one that really interests our community, because in our community, okay, we have a system here, let's say, which is our glass, that is in contact with some environment, which is above, much bigger than it. And what we want to know is what happens with the evolution of the system coupled to the environment, how it evolves in time. After, for example, we prepare the system in some condition that could be being coupled to the environment right at the time t equals 0, or changing a condition of the environment at time equals 0, not changing the glass. The material is the same. We don't change it here. But we change the characteristics of the bath. Like, for example, changing temperature, as Mark was saying this morning, or pressure, or any other control parameter that you may have in the lab. So we also do quenches. And in this context of the open system now, the quench will be a change in the parameter of the bath, for example. Could be temperature initial that goes to temperature final, and then we want to see what happens with the evolution of the system in contact with this new bath at a different temperature T final. Okay. Now, if an open system like this manages to reach equilibrium, we know from statistical physics that we can treat the coupled problem, or we never do it actually, but we sometimes at the first lecture of statistical physics you say, well, I have the Hamiltonian of my system, the one of the environments, the interaction. I do some expansion in which one neglects the interaction, considers the system being much smaller than the environment, and obtains a Gibbs-Boltzmann distribution for the properties of the system in contact with the environment, and the properties of the environment are in this beta here, which is the inverse of temperature, right? So in this way, one derives or one argues for deriving the canonical ensemble from the microcanonical ensemble of the full object, environment plus system plus interaction, which is described by the microcanonical distribution of the closed system. Okay, so this is equilibrium statistical mechanics, but if we do quenches, we don't know if we are going to reach that equilibrium distribution after some time, and the aim of these talks will be actually to describe the dynamics of classical systems coupled to classical environments. So consider this kind of total Hamiltonian over there. I'm going to do classical dynamics, so it's going to be Newton dynamics for the full ensemble, and from those Newton dynamics I will derive, in the third lecture I think, Langevin equations that will rule the evolution of the system coupled to the environment. Okay? So this is to announce part of what's going to be the aim of
What is C and what is T?
C constant. CT, it just means constant. Yes, please ask me questions. I'm very happy to interrupt it all the time and ask me whatever you feel is not clear. Okay? So in this, what I wanted to signal with this line over here is that the energy of the full ensemble system plus environment plus interaction is constant. But of course, the energy of the system is not. Because it's coupled to the environment, there can be exchanges and there are variations of the energy of the system due to the coupling to the bath, of course. Okay, so in and out of equilibrium. Consider that I couple my system to the bath at a given time, t0. I let it evolve, and I see whether a distribution a la Gibbs-Boltzmann canonical is reached or is not reached. This is the question. And typically I can distinguish two cases, which are equilibrium and non-equilibrium, by drawing a sketch like this. I have the initial time of preparation of my sample. I have a waiting time here at which I will measure something in my system, some observable of my system, that will serve me to test whether my system will has arrived at equilibrium distribution a la Gibbs-Boltzmann or not. I will give criteria for saying that you are in equilibrium or you're not in equilibrium. Ludovic already mentioned several ones in the particular context of numerical simulations of glasses, but well, I will repeat some of the criteria that Ludovic has already explained. So, any system will have associated to it some time that I will call T equilibrium, such that if I do measurements after this T equilibrium, then all my observables will be like those that one expects in equilibrium. All the criteria of Ludovic and mine will be satisfied, and the system will be in equilibrium. And in the opposite case, in which the measuring is performed before the equilibration time, then I will be out of equilibrium. Okay, so this TX here is, I'm trying to use this thing. It's an equilibration time. And its value will depend on the problem, of course. For certain problems, it will be very short, independent of the conditions of the bath with which I put it in contact. And I very quickly will be able to go beyond this equilibration time and see equilibrium dynamics. For other problems, it will be very long, go beyond the experimental times, and not be possible to reach it in an experiment. Okay, so this is just a sketch, of course. Now, let me list a couple of conditions to be able to reach equilibration. This doesn't mean that the system will reach equilibration, but these are necessary conditions to let the system have the possibility of reaching equilibrium. So the first one is that the bath itself should be in equilibrium. So the bath should satisfy certain properties that we will see which one they are when I will show you the derivation of the Langevin equation in the context of Langevin processes. For other problems in which the bath may be more complicated, these may be also more difficult to identify. In the case of the Langevin processes, they will be very easy to pinpoint, and their origin will also be easy to see. But in other cases in which the environment is modeled by, I don't know, spin variables or electrons or other things, then it might be a little bit complicated to be sure whether the environment itself is in equilibrium. But to give the possibility to the system to be able to perhaps reach equilibrium in some time, after some time, you need the bath to be in equilibrium. Another condition is that the forces that may act on the system, all the internal forces, I don't know, Lennard-Jones forces or whatever you like, should be conservative forces, so derived from a potential. I write them here like a force being the gradient of some potential V. Doesn't matter its form, but the forces should be of conservative kind. Yes?
Is magnetic force allowed?
Is it so?
Magnetic force allowed?
Yeah, it will. Yes. A magnetic field, yeah. And then you have to say something about the initial conditions. So there, the point over there that I mentioned, it was the initial condition. Something you can do is, for example, consider initial conditions sampled in some way, so chosen from a probability distribution themselves. And for example, you can choose to take your initial conditions from the equilibrium probability distribution itself, the same that corresponds to the equilibrium of the bath with the same temperature. But you could also think about taking initial conditions sampled with a different probability distribution. And then it's not so obvious if the system will be able to equilibrate or not. Then the question of the equilibration time appears. So if I initiate my dynamics with a condition that doesn't know anything about the equilibrium configuration, the equilibrium distribution, of my system, then I have to check whether this equilibration time is short enough to be able to go beyond it and reach equilibrium or not. Okay. We'll also see the role of initial conditions in the third lecture and in the fourth lecture a bit more in detail. In the third in general, in the fourth in a concrete example. Okay, so two properties of equilibrium, two properties to check equilibrium are listed here. Ludovic has already mentioned them, but I wanted to insist upon these. The first one that I list on this slide is that what we call in the literature of glassy systems one-time quantities, so quantities that depend on a single time. For example, could be kinetic energy, or could be I don't know, potential energy, or could be magnetization for a magnetic system. So those objects should be independent of time. Should be independent of when you measure them on this time axis to have an equilibrium situation. It's not a sufficient condition, as already Ludovic stressed, but it's a necessary condition. If you have one object that has an average that is not time independent, then you are certainly sure that you are not in equilibrium. Other conditions concern correlation functions. And you saw lots of correlation functions in time, delayed situations in Ludovic's talks, and you will see more today. So what do I mean by this? Imagine that you measure some observable at the time tw, and then you measure the same one or another observable at a later time t. And then you correlate the two observables by computing A of T1, TW, and A2, let's say, of T. And this object here should be a function of the time difference between the two. Otherwise, I'm sure I'm out of equilibrium. I haven't defined in this slide what are the angular brackets there. So the angular brackets and the notation psi that I'm using here are motivated by the fact that I'm thinking about the Langevin process. And so the psi would be the noise in the Langevin process, and the angular brackets would be the average of this noise. In a concrete experiment, the angular brackets would mean different realizations of the experiment under the same conditions. So you average over different realizations taken with the initial conditions taken from the same distribution, the relative odds, repeat, repeat, and repeat. You make averages. And then by making those averages, you check whether these things are a function of time difference only or not. This is, again, a necessary condition, but it's not a sufficient condition either. So there are other checks which are more detailed or finer in a sense, and that I'll mention later in these talks and during my talks. So proof of these two conditions will be given, or at least hinted at, during my third lecture. I just wanted to mention them here. Yes? Not necessarily. No, this is why I used under labels here. Could be different observables. So you could, want to correlate, I don't know, the magnetization with the potential energy at different times and see whether these correlate in a way that is stationary or not. So this property is called stationary. This is the name I used in the slide, but we also call it time translational invariant. In the literature, so this is why I write it here. Other question? Yes?
Yeah, so the time translational invariant, is that valid for every realization, or is only meaningful to consider the
On average. You need to average, yes. Because if you don't average, you will have fluctuations, and then fluctuations, can do very complex things. No, because you will see there are other detailed balance between correlation functions and linear response functions, which are not defining for the moment, but they will later, that you have to satisfy in equilibrium. So there are situations in which, for example, you reach a steady state, a state in which I define by a state where these conditions hold, but then you measure the relation between linear response and correlation functions, and those are not the ones that equilibrium asks you to be. So you can have a problem which is completely stationary, but however, it's out of equilibrium. And this means basically that the distribution function that you will have is not of Gibbs-Boltzmann form, but it's stationary. It doesn't depend on time. But it has another form. And this other form implies that these relations between responses and correlations are not the ones that Gibbs-Boltzmann tells you should be. Yes?
Do you have some precision about what the A can be? Like, for instance, it can also be some exponentially large in any quantity, or this?
Ah, okay. Or the one, you mean? No, I don't think it's necessary. No, I don't think it's necessary. No, because I'm thinking about the proof, and the proof goes through Fokker-Planck equation, and you don't need to ask any special feature for that.
A could be something exponentially big and that would be dominated by just places in time.
I don't think so, but okay, we can try to think about the... No, the question is whether there are special conditions on the observables A that I'm using here, whether they should, in a macroscopic system, not scale exponentially with n, for example, the number of degrees of freedom in the sample or things like this. So for sure, if they are macroscopic in the sense of being proportional to n, like the energy, it's fine. I don't see any problem. Now exponentially, I don't know, but I don't think there's any problem either. But we can, I will check it, but I don't think there is. What do you think, Guillaume?
No, I would say that this is valid for a finite system. For a finite system, all observables.
Yeah, but it's also for an infinite system. Well, okay. You have to prove that you go to equilibrium and so on and so forth. Yes, it's true. Okay. Okay, so let me go to the examples. The examples I want to discuss are of different kind. So the first one is just a trivial example. It's diffusion, so it's Brownian motion. It's a Brownian particle in contact with the bath, with a liquid, and then you let the particle go and see what happens. And I will argue that in that case, the equilibration time is infinite, if the particle is not bounded to move in a finite volume, in a finite region. We'll see why I say that. Other examples which are of more interest to us are cases which are macroscopic, so cases in which the equilibration time depends on n, the number of degrees of freedom in the system, and you take a large n limit, and in that case, since this equilibration time for those problems grows with n, then this time becomes very large, much larger than the experimentally observable times, and then you are out of equilibrium. And this is the example of coarsening systems. These are the simplest to see, but also the cases of glassy physics, as you will see. And then there are the cases where the forces that you act on the system, that you have on the system, are non-potential. So for example, I think that Ludo also mentioned sheared problems, so problems that you have a slab, for example, with a liquid, and you push one and the other, so the bottom and the top, in the opposite direction, so you're exerting some force that is not defined in the middle of the slab, and then there is the impossibility to write the force as the gradient of a potential, and then the conservative condition is no longer satisfied, and these are the case of sheared liquids, vibrated powders. You are injecting energy, active matter, because you are also injecting energy in the samples. So why do I say that Brownian motion is a problem that is out of equilibrium? So I have a few Brownian particles or traces. These are in the snapshot, the green dots over there, and they are embedded in a liquid. And if I want to describe this problem with the simplest possible approach, I go and look at the Langevin paper, which is very nice. And again, it's an old paper, but it's very well written, that proposes an stochastic equation to describe the motion of the particle. So I will derive this equation in a different way in the third lecture, but following Langevin, I take it like a phenomenological description of this problem. And the equation has the structure of Newton's equation, only that the force has a stochastic component and a friction component. So the force has the psi, which is the noise, the stochastic component, and the first term on the right-hand side of the equation, which is the friction component. So gamma naught is the friction coefficient, psi is the noise, and Langevin tells us take the noise to be an object with zero mean at all times, and delta correlations. So correlated noise at different times is proportional to a delta function times a factor which is tuned in such a way that gamma naught is the same that appears over there, and kBT, the temperature of the bath, appears as a prefactor, and there's a factor of 2 that is needed here. Why is this factor here? So from the Langevin argument, the factor is there to ensure that the kinetic energy, which is the only energy that the Brownian particle has, approaches, independently of its initial condition, approaches the equipartition expectation, which is that the average of v squared times m is equal to kbt. If we didn't include this factor of 2, or this gamma naught, or not kbt there, but some other value, we wouldn't find that asymptotically this kinetic energy goes to a constant, but the constant that is the equipartition 1. So the equation was tuned in this way, and the balance between the noise and the friction was chosen to ensure this property. So this is nice because the velocity of the particle is going to equilibrium. It's a quadratic variable. You expect it to reach Maxwell's distribution. Maxwell's distribution for the velocity tells you that the equipartition should hold, and this is the expression of equipartition. Now, what happens if one looks at the position of the particle instead of looking at the velocity of the particle? So there is no potential acting on the position, because I imagine that I don't have walls. Okay, this is the trick. Imagine that you don't have walls. System is infinite. So then the potential is 0 everywhere, going to infinity on one side and on the other. If you compute the average of x squared, you will find that it goes to a linear function of time, diffusion, right? So there is a prefactor, it doesn't matter what it is, but there's t here. So my first condition of equilibration, which was that 1 times quantities should approach constants, is violated. It's no longer true. It's not true in this case. So in this sense, I say that for an infinite, no boundaries Brownian particle, then the position of the particle is out of equilibrium in this sense. So this example is nice because I see the coexistence of two variables in my problem, which they're roughly the same, of course, because one is the position of the velocity, one is the derivative of the other one. But still, if I look at them from a phase space point of view, in which I consider momenta and positions as the two objects that I have to look at, then the velocities or the momenta behave very nicely, they equilibrate to Maxwell's distribution, but the positions don't. And this is something that we see, and I guess that perhaps it was also mentioned in previous lectures, that in all these glassy features, if one looks at properties of the velocities of the particles, one doesn't see anything very special, right? While when one looks at the positions and one starts asking questions about the structure or dynamics, focusing on density properties, which are linked to the positions, then one realizes that there are very special features going on, and that there's out of equilibrium dynamics that I will describe, and so on and so forth. So this example I choose to mention because it shows this coexistence of variables that behave very differently concerning reaching or not reaching equilibrium. Leo.
But for this limit, you take it the limit that you forgot about the initial condition, right?
Yes.
But in that limit, still time correlators depend on the difference.
Depends which one you look at. If you look at, not all of them. For example, if you look at x of t prime, this one is proportional to the minimum between t and t prime. So it's not stationary. Instead, if you look at x of t minus x of t prime squared, this one goes like, 2d t minus t prime. Okay, so it depends on which one you look at. But to claim that you are out of equilibrium, it's enough to have one that is not stationary, right? Yes, it is, yes. But in my head, I always think about t being larger than t prime. So always in my notes, t is larger than t prime. Yes?
The definition of being equilibrium, do you have any constraint on what kind of observable age that you're talking about? We are talking about extremely microscopic variable.
No, I mean, well, in this case, I just have one particle, so I have two possible.
Right. But conventionally, when we talk about a system in equilibrium,
yes,
I guess we usually refer it to some macroscopically observables, which independent.
Okay, so next I will go to macroscopic systems, and you will see, in macroscopic systems, how they can be out of equilibrium or not. But this example is, it's just one example, which is this is why I said from single particle to many bodies. So this is a single particle example, and that I think it's illustrative of the fact that you can have different variables behaving very differently in any system, in particular in this one, which is kind of trivial, right? Yes. Okay, this is an inertia time. I will discuss it a little bit more in one of the third talk again. It's just the time that you need to go beyond to reach this limit. Okay, otherwise, if you look at times which are shorter than this inertia time, there will be some time dependence of this object over here. There will be some exponential dependence that typically will tell you how the memory of the initial condition is lost. And this exponential has a time scale in it, which is that object over there. No, it's not. It's not. This is just a characteristic time for the decorrelation of, or for the decay of the observables linked to the velocity. It's just that. There was another question, yes. It's an equilibration time for the velocity.
So in one of your previous slides, you mentioned that for dynamics in equilibrium, you need to have only conservative forces.
Yes.
However, if you just have damping and no like Gauss finger, still equilibrate, right?
Okay, because yeah, exactly. So I didn't explain it well enough. So when I said conservative forces, I was meaning forces that correspond to the system, right? Forces which are internal to the system. This frictional force has to do with the coupling to the environment. So this is the one that allows me to give extra energy that I have perhaps in my initial condition and leave it to the environment, to the bath. Was another question someone there? Yeah. Oh, they will behave stationarily. So they will behave as in equilibrium. So everything you will like to measure for the velocity will behave well in the sense of equilibrium. So if I measure, for example, this will be a function of T1 minus T2. Always at time scales, T1 and T2, that are larger than this inertia time. There I call it TVR, I will call it TI in the rest of my talks. Well, it will disappear quickly, but it's this quantity here. Yes?
So how does the kinetic energy react to the equal partition?
Exponentially.
Exponentially.
Yes. So this is why it's a well-defined relaxation time. There will be exponentials like this, for example, with the initial condition. Yes. A noise that makes the x's equilibrate and the v not and the v don't. No, I don't think so, because this depends on the potential, right? So the noise will help you. Let me see. Okay, let's think about additive noise. Yeah, a Langevin equation with a noise which appears like an additive force. In those cases, I don't think you will be able to equilibrate because there is no potential to equilibrate too. You see, in the Boltzmann factor should be this. But if v is 0, this is 1. And if I don't have boundaries, if I don't have boxes, if I don't have endpoints in my space, my x variable is unlimited, and this cannot be normalizable. The integral of this over infinity will give you infinity. So you cannot have a normalizable distribution in equilibrium in this case. No, then of course, if I put a potential like any form but a harmonic potential, for example, then there's no problem and I will reach equilibrium in a time scale that for the x variable and the v variable will be different. So this will still be the one of the v variable, and the one of the x variable will have a dependence on k, of course. So it will be dx, let's say, let's call it like this. Maybe proportional to 1 over k squared. They will be different. timescales, but it will be finite in that case. So you can do the exercise. If you want to do exercises, compute this T equilibration of x in this harmonic case. Okay, so coexistence of two kinds of variables. This is what I wanted to stress with this example. Now macroscopic systems. Okay, so 3 examples: domain growth, phase separation, systems with quench disorder, and system with frustrated interactions that will belong to the same family, let's say. I will discuss now. So this is the simplest possible case. Imagine that you have a mixture of 2 species. Draw them, with blue and yellow over there, and you mix them, and then you set the system under conditions such that the mixture will like to separate. So the blue would like to go with the blue, and the yellow would like to go with the yellow, like water and oil, let's say. Or there are binary alloys, and many, many different examples that belong to this class of system. The question is, how does this phase separation occur in time? Because there is an initial time, like here, where I put my mixture perfectly mixed under conditions such that the 2 species will like to separate. And then what happens next? And what happens next is that there is this process. It depends on how you prepare your sample, which are the parameters in the problem, but let's look above, just the case above. So I start from a mixture of blue and yellow that gives green, and I let it evolve, and what I will see is that regions which are more yellow-like and regions which are more blue-like will start to appear in different places, and the blue will become more blue and the yellow will become more yellow as time goes by, and then again, and eventually, very late after this process started, I will have perfect phase separation between the blue and the yellow. But this will last very long. And for this problem, I will give you arguments tomorrow that tell you that the equilibration time, so the time needed to go from the green to the blue and yellow, grows with the size of the system in a way that scales like a power law of the system size. Okay? So the equilibration time in this problem goes like a power of L with an exponent that conventionally is written like 1 over ZD. ZD, a dynamic exponent. Okay. There is a prefactor that depends on temperature, other details of the problem, but the important part is this one. And this means that this, for systems that grow very large, goes very long as well, and can become, for sufficiently large systems, longer than the experimental times. Okay? So another example of the same kind, but it involves glasses, although the glassy aspect of the problem is not so important here. These experiments done in Paris where people mix, I can give you the composition, but okay, I don't remember it. So mix components, and these components will like to make 2 glasses. And so you see here in light gray and in dark black, let's say, regions where there is 1 glass and another glass. And in the course of time, these 2 like to separate, and then you can see pictures like this. And people are using this in Saint-Gobain in France, for example, because they want to, I don't know, tune certain properties of glasses, and the structure of the domains in the system is important in the mechanical properties of those glasses, and they want to reach, certain sizes which are especially good of this phase separation.
What do you mean by this kind of glasses?
It's just that if you had this gray thing alone, it could be a glass, and the black thing alone as well. They're different glasses, but they want to phase separate.
How do you differentiate?
Sorry?
How do you differentiate 2 different kind of glasses? Because
because they have different optical properties and mechanical properties and macroscopic properties. Somebody told me about macroscopic properties. They're different. Yeah. It's not that I claim that microscopically people go and look at the structure. Probably they do as well, but they're microscopically different in the sense that they have different properties. Sorry? Also, well, they are. Okay, so now what happens if you want to discuss quench disorder? Because here there is nothing that I could associate to variables in the problem that stayed fixed, didn't evolve during my evolution time. So quench disorder is an expression that is used to describe variables that are frozen during the time scales over which other variables fluctuate. So it's like saying that there are certain variables in your problem that evolve during all these times here, but there are other ones that don't. So this is the case of spin glasses. I don't know if somebody explained already what the spin glasses are, but let me say it in 2 words here, the real ones. So the real ones are magnetic alloys, typically. So this is the real system. And then you have impurities there, magnetic impurities. I will draw this way. So in the bulk, there is something else. I don't care what it is. But these big dots here are magnetic impurities. And so they have a spin attached. So imagine that they are easing spins, that they have a preferred axis which is vertical in my drawing, something like this. So during the time of the experiment, the positions of these impurities don't change. And this is what is expressed as being quenched. They're fixed. But the spins are not fixed, so the spins can flip. So they can become the opposite direction during time. So they can flip. So you have here a combination of 2 variables, if you wish. Ones are the positions, which are fixed, and the other ones are the spins, which can flip. Now, since the interactions between the spins depend on the distance between the spins, so there is a potential of interaction between the spin I and the spin J, which is a function of the distance, which I think I wrote it in the next slide. Let's see. Yes? It's proportional to this function, which depends on the distance between the 2. So this prefactor is independent of time, because the positions are fixed. And then there is the usual, so this is the prefactor there, so let's call it G of R, times SI, Sj, the usual interaction between spins. So this part, of course, changes in time, but this one doesn't. But now, since the positions that these impurities occupy in the sample are random, because of the way in which this sample has been prepared, then these prefactors here are random. There is no crystalline structure at all there. So what people have done to mimic this randomness is to replace this distance dependence by just an exchange constant here that is random, taken from a PDF. And fixed. Doesn't change during the calculation nor during the experiment. So I'll give you more details about the models of spin glasses later, but the justification is just this line over here, and the quench randomness is the word that is associated to this fact that is fixed, random, and you see the values of these Jijs will change because of the fact that this G of R will change, and they are not all the same, and they don't have the same sign either, because the sign over there can change sign. So there is no ferromagnetic or antiferromagnetic bias. There can be both kinds of interactions in the system. Okay, so these are problems that have been studied a lot in the literature. They are all these very nice connections to informatics, optimization problems, and so on, that are being discussed in these lectures. I will give a little bit of detail about the experimental measurements in spin glasses, not so much, but to make the connection or show some differences with the behavior of other kinds of glasses in these talks. So glasses, they are of many kinds. Structural glasses, you heard loads of talks already about them, so I will not spend a lot of time on those. I will jump this. So let me say what we do not know about these problems, focusing on the dynamics, and what we would like to understand about these problems. So, did I write that? So all these, already the phase separating problems remain out of equilibrium over very long times. These problems with competing interactions, why competing? Because in this problem here, some spins will feel ferromagnetic bias, some other ones will feel antiferromagnetic bias, will try to anti-align because of the sign of the Jij in front. So there is competition of different kinds of interactions in these problems, and this leads to what is called frustration. So in these kind of problems, glassy systems of a structural kind that you've seen, but also on those over there, it's not so clear whether there are actual phase transitions. In the community of spin glasses, nowadays, consensus is that there is a phase transition of equilibrium kind at a given finite temperature in 3 dimensions. But it was discussed in the literature for decennies. The opinion was, Federico is laughing back in the row. There is not, with a period of 7 years, I would say, roughly. Okay, so it's not so easy to decide whether there is an equilibrium phase transition or not in these disorder problems, because simulations are difficult, experiments are difficult, and it's not so obvious. So, but at least, let's assume there is a phase transition. It's not so clear either what is the nature of the phases at low temperatures. Okay, the high temperature phase is easy, it's paramagnetic, but what's going on at low temperatures is not clear. And again, different groups have different feelings about this and believe different things. So it's an open problem. I would say it's still an open problem. Concerning dynamics, which is my main interest in the talks, what is the mechanism that leads to the relaxation that is observed in these problems is not clear either, okay, in the real finite dimensional system. I will discuss some models that we can solve, which are mean field, that reproduce certain aspects of the experiments, but of course we never know if the mechanism can be very different in real life. So this is still quite open. What do we have as analytical tools to deal with this? We have what I would call dynamic mean field theory, models which are of the same kind of the ones that Florent and Guillaume were discussing, models where spins are connected to every other one. In the sample, there is no notion of distance. In the samples, those can be solved. And those give, as I said, certain aspects of the real experiments that what is good, but we are not sure that these are the same mechanisms as in the finite dimensional case. So just very quickly, I will give you examples of cases where you have forces that don't derive from a potential, where you can reach steady states, but they are still out of equilibrium. So those are the cases of rheology, for example, where you force in some way your liquid, for example, with a rheometer, like here, or when you do transport, even in quantum systems, you know, couple your system to two reservoirs, two environments which are different, and you let a current of particles or a current of heat go through, and then you want to measure something in your system. So you can reach a steady state in this way, but it will be out of equilibrium. It's forced by the coupling to these two different baths, which are not in equilibrium, them. They could be, this one could be in equilibrium, that one could be in equilibrium, but the ensemble is not. So rheology of complex fluid is a full field. I will not touch upon that one. Another case which is interesting, on which Leo worked in the past, is the case of interfaces driven over, for example, a rugged landscape. So you have a disordered landscape, like this, sketch over there, and imagine that you have, I don't know, water on the left that has to go over and, you know, invade what's on the right, and you're pushing this with some force, and you want to know, you know, how long it takes, what is the structure of the interface, and, you know, many different properties of this kind. And these problems have glassy features linked to their disorder in the substrate. And, well, there's a lot of nice things that can be said about this. I will not discuss them either, but it's another example of disordered-driven problem, because I'm pushing from, or pulling, better said, from the interface. Yes? Sorry? Because you have to think about, imagine the line as being an elastic object, for example, and that you have this elastic object that is sitting on a mountain landscape. And you want to take this line, take it down the hill, but you have mountains, I mean, they have peaks that do not let it go. It has to go over the peak to go on the other side. So the disorder is fixed, is the landscape of the mountains. And you can have statistical properties of this disorder, and you can try to understand how many different lines will fall down the hill because of the gravitational force, let's say, and how they will do it. You know, there will be jumps over the barriers, there will be moments in which they will be pinned, there will be an effect which is called the pinning, actually, how much you have to pull from your interface, from this line, to let it slip and go down. Otherwise, it will be pinned. If C is like a critical point in this problem, yes. Well, creep is what happens is the name is given to the velocity against the force characteristic plot, or characteristics. And this is the behavior that you find is called creep at final temperatures, because there is no critical force. It starts with a weird functional form that has been computed. And okay, this is what is called creep. And the pinning is the phenomenon where you need a finite force to make the interface move. And there are glassy features linked to the disorder of the substrate of the mountain. Okay, active matter, well, let's jump. We saw this. It's another example of a driven problem where there is energy injection, and there are different scales, and it can be done artificially. There are many things to say in this context, but I will not. So in these lectures, we are going to focus on problems in which there are no weird forces. There's no injection of energy, no activity, just relaxation and noise. So let me give a little bit more details on the glassy aspects that we would like to understand. Here it is. So many of these statements have already been said in talks. I repeat them here because they are the ones that interest me. So in the case of structural glasses, there is this TG that Mark described this morning in a lot of detail, that looks like a mixed first and second order phase transition. And I will explain why in the dynamical context this is seen as a mixed first and second order phase transition. So it's kind of a strange object. It's not, first of all, it's not really a transition. because as Mark was answering to Gregor's question, how do you define TG? It's not even very well defined. It depends on the cooling rate that you use to measure. So it's not really a transition. But there are certain aspects of what's going on at TG in experiments that look like a mixed first, second order phase transition. The spin glass one, no. The spin glass one is more like a conventional second order phase transition if it exists. But exponents have been measured. There's nothing like this mixed character of the structural glass case. Now there is a family of models that I will describe that capture these two cases with different choices of parameters in those models. And all these models are models of spins coupled with interactions, which are generalizations of what I've written here, but that can be treated with methods of theoretical physics that are well controlled, right? So we know the limitations that these models have. We know what should be done to improve the solutions of these problems. But of course, this is difficult, so we don't really know how to do it. But at least we know which are the directions that one should take. And as I said, we have static and dynamic analytic methods to study them in the mean field limit, and we would like to go a little bit beyond the mean field limits, although it's very difficult. So this you heard already. This you heard already. This you heard already. So two-time observables to check for equilibrium or non-equilibrium behavior. So this is the same sketch I've done before. You have one observable, another observable, you want to correlate them, and you want to see, as a first check, whether this object, the correlation, depends on the time difference or not. So in the case of liquid glasses, let's say supercooled liquids that become glasses, the natural observables are density-density correlation functions, their Fourier transforms, their self-part. Ludovic explained and defined all this. I will not define them again, but this is the kind of objects that we will look at. So these are the way in which these correlations behave above TG. You saw this already. So the relaxation time increases when you go down in temperature. This is a, what is it? A molecular dynamic simulation of silica. This is experiments in glycerol. They look similar. Same kind of qualitative behavior. There is no change in the structure, like Mark said this morning, while there is a big change in the relaxation time. If you look at the structure, it doesn't change that much. Now what happens, one more thing that I want to mention is that if I look carefully at these curves, I see that at sufficiently low temperature, there is like a plateau that develops and then a further decay. And so this is a linear logarithmic scale. In this scale, you see, look at the last curve over here, that there is no change in the first time regime here. Then there is, this going down towards a plateau, and then it goes down again. So the sketch of the correlation function at sufficiently low temperature is something like this. Right? And this is time delay. And this is that correlation function. So I see a plateau. I will call it Q here. We call it QA. Let me call it QA. And I see that nothing seems to stop the development of that plateau. There is no, if the simulation could be done at lower temperature, it seems that this will become flatter, and I will do something like that, right? At least one could be tempted to say that this could occur. Now, what is the explanation or one interpretation of this plateau? Yes? I'm above TG. So this is, I'm still above TG, yes. So they are all different temperatures. I'm going down in temperature. and I don't see anything special, no accumulation of curves going on. And then, of course, in the simulation, what happens, but it will come into more slides, is that if you go to lower temperatures, you cannot keep your system in equilibrium. So you cannot pass all the tests of equilibration that a good simulator should use. And then you will see that the system falls out of equilibrium. And I will show you next what happens. Yes?
What's the physical intuition behind
The plateau?
point where it plateaus? So why does for different T's it plateau at the same point and not at different?
Okay, so let me go here. Next, I don't know, Ludo, had you explained the cages and so on? You mentioned them. No, nobody did. You said something? Okay, so the kind of hand-waving explanation that is given for these cages in the case of these particle systems is the following. So Mark showed them today, I think. So these are just traces. So you pin one particle, you look at one particle, and you see how it moves. Okay, and you draw with a line. Well, you join points at which you measure this particle with lines, and you see something like this. So what you see is that there like regions where the particle moved, localized, let's say, and then there was a jump somewhere here, and it went somewhere else, and it moved somewhere else, and so on. So the idea is that if you look at correlations between times which are not very far away, what you are measuring is the correlation within one of these cages. So a cage is a word used for saying, well, the particle is rattling very quickly there and it doesn't go far away. And this is what you see here. Now, if you look at time delays which are sufficiently long, of course, the particle is not completely confined to be within a cage because it's not a crystalline structure. There is relaxation, structural relaxation, and so on. So what's going on here is that here you go away from the cage. Of course, each particle has its own cage. Nothing is static. Everything is moving. So it's just like a picture to justify what's going on. I will give a maybe clearer explanation of the equivalent of these cages in ferromagnetic systems in a second.
My question is that, so this happens, let's say, at 0.5 pp, and I went to then 0.48. At 0.5 pp, the Fs had a plateau at 0.8, let's say.
Yeah,
so at a little bit lower Tg, why is not plateau at a little bit higher position?
Okay, so because this is like another parameter. This is the it's working like it's functioning like another parameter for your transition. So it's a very special property that you're approaching. It's like approaching a transition from above, and then you're how would I say it? It can only have one value, right? So if you think about it as another parameter that it's of a first order phase transition, this is why it's finite. Okay? So if you interpret the QEA as another parameter, sorry, of a first order phase transition, then it has a value, it has a number. Otherwise, what you could say more intuitively, or thinking more in terms of particles and not in terms of other parameters, is to say that well, the cages are all the same, and you're approaching cages that will all behave in the same way, and you are approaching those at short time distances, and what you will change with temperature is the lifetime of those cages, but not the property of them. This is So the lifetime you do change, of course, because if you look at high temperature, this will decay before, but not their stiffness or their size. Other questions? Okay. Other measurements can be done doing perturbations on the sample and measuring linear responses. And I will come back to linear responses later on, but I just want to mention that this plot that Mark showed this morning, I also had it in my slides, it's a measurement of a response, right? While this measurement that I showed here is a measurement of a correlation function. Because here I didn't perturb the sample, I just compared the configurations, the density values at 2 different times, and I constructed this thing. So this is a correlation function that measures spontaneous relaxation in the sample. While that measurement over here is the response to a field oscillating, in this case, with a given frequency. So I'm doing something on the sample. So this is an induced relaxation, induced by the perturbation, right? So this is the response, that's a correlation. And in equilibrium, we never think about the difference between the two. But out of equilibrium, one has to be careful. And it's linked to your question again. What will happen in the glassy phase is that there will not be a direct, obvious relation between the two. The correlations and the linear responses will behave in sort of independent ways that are not dictated by any measure, by any equilibrium consideration. There will be comparisons between the two that will be interesting and will give you information about the behavior of the system, but it's not obvious a priori. So a priori, one has to think about responses and correlations as different objects and see what happens with them in a simulation or in an experiment or in a calculation. Now, what happens if I go down in temperature? So here, I was just talking about temperatures which are above TG. Now I still go down in temperature. And my claim that the first guess would be that this goes on and I always be able to equilibrate and get a longer and longer and longer plateau is not true. What happens is that when the experiment or simulation goes below TG, then the equilibration time goes beyond the measuring time. So in the sense that in my plot over here, my equilibration time came somewhere here. I don't know, but certainly beyond. It's a function of temperature and system size. Above TG, I had it somewhere here. But below TG, it went beyond the times that I can use in a computer or in an experiment. And if I measure the same object now, I measure correlation functions, but now at fixed temperature and at different waiting times. So I'm choosing the waiting time, I'm letting time evolve. I draw one of those lines over there. I choose another waiting time, I let time evolve. I plot another of the lines over here. And what I see is that the different lines don't fall on top of each other. So if they don't fall on top of each other, what it means is that the correlation function is not a function of the time difference. So this one I cannot pull up, sorry. So what this means is that that correlation function at t smaller than tg is not a function of t minus tw. It is a function of the two separately, because I see that depends on t weighting, different lines, and it depends also on t minus t weighting, right? This is for a simulation of a Lennard-Jones mixture. This is for colloids. It's seen in many different glasses. It's quite universal. What do I have to mention here? I have to mention that I still see the plateau. So if you look at the, let's look at the red curves over there. It's more clear, perhaps. It's clearer. So I see the plateau. I see the plateau. But now again linked to your question, if I look at different temperatures, I will see that the plateau depends on temperature. So for one temperature, I will see something like this for different T weightings. So this is T weighting 1, T weighting 2, T 3, and so on. And for another temperature, I may see something like this, or going up. Okay? So this is for T1, this is for T2, and actually T1 is smaller than T2. And you will see why later on. Okay, so now below Tg, Q, EA, is a function of temperature. And the value that I was telling you that it didn't depend on temperature above Tg is because I was looking at the limit in which I was taking T going to Tg. Right? Okay. So, aging is the word that is used linked to this problem because the relaxation is slower the longer the waiting time. Okay, these curves are ordered in such a way that the waiting times which are longer are to the right of the waiting times which are shorter. So I need a longer time difference to reach the same decorrelation value for longer waiting times. So here I'm plotting. I'm using the notation of the waiting times, so I should do that. So what I'm saying is that if I cut these figures at this height, you see that I need a longer waiting time to reach the correlation, let's say 0.5, for the longer waiting time than for the shorter one. So the relaxation is slower for longer T waiting. This is the meaning of aging, and this is what is observed in all these glassy systems below Tg. Also in, I can jump. Also in spin glasses below Ts, the critical temperature. And these are experiments where people have looked at magnetic correlation function for different waiting times. So this is correlations. And this is linear responses, so what is called thermoremnant magnetization. You apply a field and then you cut it at different waiting times. And you see how the magnetization decreases in time after having switched off the magnetic field. And you see, again, the waiting time dependence. So I still have 5 minutes. Let's see what I had. Yeah, there's also seems to be a plateau in these curves. Maybe it's inclined, maybe not. But okay, there is something like certainly a separation of time scales. So this is another keyword I want to mention here that will come back later in my talks. So these plots are showing a separation of time scales with a fast relaxation to plateau. Why do I say fast? Well, because it occurs in this regime. So you see all the curves here go relatively fast to the plateau. A slow relaxation from the plateau. Below the plateau. And the fact that this fast relaxation is stationary, in the sense that in my drawing here, all the curves come together. I just showed one, because they are all together in this sketch. While here, there is really the waiting time dependence below the plateau. This is where the curves deviate one from the other one. So here is the waiting time dependence. And there's, in the sketch, there is a very neat separation between the two, given by this flat plateau over here. In the experiments, of course, it's not so clear, but well, there seems to be something like this as well. You see the time scales here at the beginning, where everything goes together, all the curves are together, and the opening up of the curves below the plateau, where the waiting time dependence appears. So, these features that might have seemed a little bit bizarre in the context of glasses at the beginning, actually, they also appear, and one understands very well why, and this will be the content of my lecture tomorrow, in problems that do phase separation or domain growth. So what I'm showing in the left plot here is just the correlation function between the spin and the spin in an Ising model in 2 dimensions, quenched below its critical temperature. And you see that the correlation functions have the same waiting time dependence with a plateau, which is very clear in this case, and that one can understand very well. And I will explain tomorrow what is linked to, or how it can be understood in the context of the 2D Ising problem. So qualitatively, if I compare these plots with these plots, they are the same. Of course, quantitatively they are different, but yeah, they have the same global features, right? So there is also aging and these waiting time dependencies and so on in a problem as simple as the 2D Ising model. Now, I don't claim these problems to be the same, and actually the differences will be in the response functions. So this is why I want to stress that correlation functions and response functions are not the same. They can behave very differently in problems which are out of equilibrium. And well, we will see this later. Now, I see that I only have 1 minute. I had a lot of other things to tell you, but let me see. Well, I think I can stop here. Yeah, I had the responses. I had this. Well, this I can jump. OK, so let me just finish in this way. So I just showed you pictures and talked about phenomenology. Now let me tell you in a couple of words which are the things that we would like to understand here and that we haven't understood yet, or what is, open problems in this context. In the context of coarsening systems, we understand very well the dynamic mechanisms, and we understand very well what is going on. And I will describe it in detail tomorrow. What is not so well understood or so well controlled in those cases are the analytical calculations. So what I mean by this is that we know which is the equation that has to be written to describe the problem, the physical problem. But we don't know how to solve it. Why? Because it's a nonlinear field theory, let's say, and there are no good methods. One cannot do perturbation theory, one cannot do RG. One can do large N, one can do mean field methods, and those work very well, and then we can compute everything. But of course, they are limited. There are certain properties that don't describe quantitatively correctly. So in the coarsening problem, if you wish, the understanding of the phenomenon is very good, but the quantitative analysis lacks some features. In the case of glasses, it's different. In the case of glasses, we don't even have such a good understanding of what's going on. There are people with different views. You are being exposed to all of them, more or less, here in these lectures. But OK, there is no common understanding of what the dynamic mechanism, if one thinks about dynamics, or if there is a phase transition, if there is not, and so on and so forth. So the difficulty is more conceptual than in the previous case. Of course, it's also computational, but it's a step before that we are at which we have a problem. Another general question that one can ask, or a general question that one can ask in both settings, is are there some kind of thermodynamic properties that these systems enjoy or have even when they are out of equilibrium? Because thermodynamics, one has to remember, is defined in equilibrium. So out of equilibrium, what's going on? Are there properties of thermodynamic flavor that can be extended to these out of equilibrium systems? There are many people who have worked on this. I'm not sure I will have a lot of time to discuss these features, but just to let you know that there are questions that have been posed, and there are some answers given as well in this direction. So This I can go over. This I can go over because I'll do it tomorrow. Yeah, let me just finish by giving you some references. So there are many review articles, of course, that treat these problems. All the phenomenological and experimental data that I showed you are pretty old, from more than 20 years ago. So the reviews exist in the literature. I just listed two here. I'm the author because those are the ones that I know better, so this is why I listed them here. The first one is about spin glasses. You didn't get a lot of lectures on spin glasses, I think, but concerning the experiments of spin glasses, we had a review in '96 where all the experiments are described. So that's the first one. Concerning theory and methods, you can look at my Lesouche notes, and for more simple issues, like the ones of the Brownian particle and so on, you can look at lectures I have in my webpage, but I also cut them in pieces and give some to Leo for the parts that concern these talks in particular. So this you will have. Concerning growing lengths, although I will not discuss them so much, but other people have done this in the context of aging out of equilibrium systems. There is also this review article here. And I didn't add references on glasses because there are other people who are much better situated than me to talk about the experiments in glassy systems. So Mark will surely give you many references in that direction. So this is concerning the references. So what I will do in my lectures is basically, concerning the analytical part, is basically talk about this frame here, which is show you how to derive or how to write down generating functionals for classical field theories of a stochastic kind, like Langevin field equations, and what to do with them. Certainly not perturbation theory, not renormalization group techniques, but self-consistent approximations, which are equivalent. So these are the mode coupling approximations or approaches that Dave Reichman will describe. But in the context of the spin problems, they turn out to be the same to the kind of equations that we get for the fully connected spin problems of p-spin kind. So let me write it in case you don't know which one it is. So all the analytical part of my talks will be about this model here, where these are taken from a PDF, Gaussian kind, and these SIs are spins that, to make the calculations easy, we make them spherical. Okay, so contrary to the models that, for example, Guillaume was discussing, or Florent as well, I will work with the continuous variables for the spins, constrained to satisfy this spherical constraint. Here I'm summing over I. And this continuity of the variables allows to write Langevin equations and do dynamics in a relatively simple way. The solvability of the problem is here. Is in the fact that we are summing over all p applets in the systems, and by choosing different p's or choosing Ising versus spherical, where Ising is modelized by soft spins, and I will describe those later. One can capture domain growth, spin glasses, or fragile glasses, let's say. And this is for p larger or equal than 3, and these two are for p equals 2. This is spherical, and this is in. Okay, so what this family of models has, which is very nice, is that with different very simple choices of the parameters in the definition of the Hamiltonian, one can have a mean field of course, descriptions of all these problems in parallel. And you will see which are the differences that arise and how these differences are in connection with the observations. Right? Okay, so I apologize for the 5 extra minutes, and thank you very much, and ready to answer questions. I don't know if you have public or private questions.